Okay, so we are back on differentiation for hyperbolic functions, and now we are differentiating the inverses. So these are actually in the formula book. So if we look here, we've got the normal trig stuff, so arc sine, arc cos, and arc tan, and then we've got all the hyperbolics over here. So this is actually in the formula book, and we can kind of like see the similarities. So like the derivative of arc sine is 1 over root 1 minus x squared, whereas for arc cos we've got 1 over root x squared minus 1, and here we've got 1 over root 1 plus x squared. For arc tan, we've got 1 over 1 plus x squared. For arctan, we've got 1 over 1 minus x squared. So we can see they are very similar. So just like with the normal trig functions, to prove arc sine, arc cos, and arc tan, we can prove the hyperbolic ones. So I'll just do r sine for example. So if you want to prove that the derivative of r sine x is 1 over the square root of x squared plus 1, what we do is we start by letting y equals r sine x. Just like in the other one where we were proving the standard result for r sine x, we can do a similar thing for proving the derivative. So we're going to get x is equal to sine of y. So now if we differentiate this, we're going to get dx by dy is equal to cos y. Now we don't have to do it implicit because we're differentiating with respect to y. We're not differentiating with respect to another variable, so we don't have to like multiply by dy by dx or anything. So dx by dy, because we're differentiating x with respect to y, is cos y. Well, using our identities, we know that cos squared y minus sine squared y is 1. So cos y is the square root of 1 plus sine squared y. So plugging this in, well, we know that sine y is x, so sine squared y is going to be x squared. So what we get is cos y is equal to the square root of 1 plus x squared. Well, we know that cos y was dx by dy, so dx by dy is the square root of 1 plus x squared. So if we just get dy by dx, we just do the reciprocal of both sides. So we're going to get 1 over the square root of, well, here it's x squared plus 1, so we'll just put x squared plus 1 because it's the same thing. So we have proved that dy by dx is 1 over the square root of x squared plus 1. Okay, so I guess these you don't really have to know because they're in the formula book, but it would be good to be able to know them. Okay, now let's do this exam question. So we have y is equal to r cos x all squared. Prove that x squared minus 1 multiplied by dy by dx squared is equal to 4y. Well, first let's differentiate this. So we'll get dy by dx is equal to, right, now we're going to use the chain rule. So first we're going to use the power rule on the outside function. So we're going to get 2 r cos x to the power of 1. And then we're going to multiply by the derivative of the inside function. So multiplying by the derivative of arc cos x, which is 1 over the square root of x squared minus 1. So times 1 over root x squared minus 1. Okay. Now if we see here, we've got the x squared minus 1 multiplied by dy by dx squared. Well, dy by dx is on this side, and then we've got x squared minus 1 over here. So what we have to do is multiply through by the square root of x squared minus 1. So what we're going to get is the square root of x squared minus 1 multiplied by dy by dx is equal to 2 r cos x. But now if we square both sides, we're going to get rid of this square root. This will become dy by dx squared, and this will become 4 r cos x all squared. So what we're going to get is x squared minus 1 multiplied by dy by dx squared, this should be in one bracket, is equal to 2 r cos x squared, which is 4 r cos x all squared. Well, y was r cos x all squared, so we can just substitute that for y. So what we'll get is 4y. So therefore, x squared minus 1 multiplied by dy by dx all squared is equal to 4y. There. we got that right. So that is pretty much it now for differentiation. So now we'll go on to integration.